All right. Hi, everyone. We're going to be presenting our research and findings from the RU we participated in earlier this summer with the University of Michigan-Dearborn. So our topic is the numerical range of a composition operator induced by an anti-diagonal matrix. All right, so here's a quick overview of what we're going to cover in our presentation. So first of all, we need to cover what the composition operator is and what particular case we're exploring. Then we're going to talk about the matrix representation of that operator. And then using the information from the matrix representation, we can find and discuss the spectrum and numerical range of CA, which is our operator. Okay, so first thing to discuss when looking at the operator is what we're operating on. And here we're operating on the Hardy space of the unit ball. The Hardy space is a space of holomorphic functions, which basically just means that the functions are complex and differentiable. The composition operator, CA, composes a matrix A with a function F from within the Hardy space. This is done by the matrix multiplication of A with Z, the input vector for F. Composition operators are not limited to being induced by matrices, but in this is the case that our project is focused on, and more specifically looking at anti-diagonal matrices. So here we can see one example of an anti-diagonal matrix where n is equal to 4, so we have a 4 by 4 matrix, and how it works with our composition operator. So we have a matrix A, which only has terms along the anti-diagonal, and our input vector Z can be split into 4 parts, Z1 through Z4. And we can see the resulting vector from matrix multiplication. Note that after being composed, the terms have gained coefficients, A through D, and the Z's have swapped their order. What was Z1 through Z4 is now Z4 through Z1. This swapping is going to be true for every n case, not just the 4 by 4. Okay, so we have our operator on the Hardy space mapping FZ to FAZ, and our goal is to find the spectrum and numerical range of this operator. But we have a problem. The Hardy space is infinite dimensional, and as a result, the spectrum and numerical range of CA can be quite expansive and difficult to characterize. So we need to find a way to split up our Hardy space into finite dimensional parts. And lucky for us, this can be done using the homogeneous polynomials. A homogeneous polynomial is a polynomial whose non-zero terms all have the same degree. In this example, every term has the same degree of 5. So this polynomial is in the homogeneous polynomials of degree 5, or H5. So these spaces of polynomials come in handy for us because they form a direct sum, which is equivalent to the Hardy space. Thus, our operator can be written in terms of the operator restricted to each of these subspaces of homogeneous polynomials. And since each HK is finite dimensional, we can find a matrix representation using the basis elements of HK, and then in turn, find the numerical range of the restricted operators. All right, so now we're going to step through how we found the matrix representation of our restricted operator using the n equals 4 case. So recall from the earlier slide that our mapping. So we need to look at how the basis elements of HK map within underneath the composition operator in order to build out our matrix. So all basis elements for the homogeneous polynomials of degree K are monomials built from Z1 through Z4 and are degree K. So here that means the powers of the Z's all sum to K. All right. So these monomials are the functions that we're going to be putting into our operator. So if we plug in this red basis element, we get out a scalar multiple of another basis element, that blue one. So notice the red and the blue elements have mirrored powers. The red has alpha 1 through alpha 4, and blue swaps those around to get alpha 4 through alpha 1. So then if I plug that blue element in to see where it maps, I get out a scalar of the red. They map to each other and thus create a subspace. This is good news for us because we can make a mini matrix using those coefficients, and that matrix maps those red and blue basis elements to each other. All right, so imagine we did this for every basis element of HK. We would have a whole list of these 2 by 2 matrices mapping basis elements to each other. We would even have some 1 by 1s when an element maps to itself. So we call these blocks. Here we have the capital B as a signifier of our block. So we can place all of our blocks along the diagonal of a bigger matrix. And this covers the whole basis of HK. So we have successfully built out the matrix representation of our restricted operator. And we wanted to do this because finding the eigenvalues of that matrix is the same as finding the spectrum of the restricted operator. We can then in turn use the spectrum of our restricted operator to find the spectrum of our operator. So the eigenvalues of our big block diagonal matrix is simply the set of all the eigenvalues from the individual blocks, which can easily be computed. So the spectrum of our operator restricted to HK is stated here on the top equation. And if you recall, the direct sum of all of our subspaces of HKs is equivalent to the Hardy space. So we can finally state the spectrum of our unrestricted operator as the union of all the spectrums of our restricted operators. And then 0 also needs to be adjoined to get the entirety of the spectrum. So that's just stated nicely here in a theorem at the bottom of the slide. And then now that we found the spectrum of CA, Tim is going to discuss the numerical range.
All right, let's start with the definition of numerical range. Letting T be a bounded operator on our Hilbert space, we define the numerical range of T as the set of all inner products of T times an element X with an element X of the Hardy space such that X has a magnitude of 1. So now for a little example of the numerical range, we let A be a 2x2 antediagonal matrix. The elliptical range theorem tells us that the numerical range of A is an ellipse centered at the origin whose foci are its eigenvalues, which are plus or minus square root of AB. It has major axis absolute value of A plus absolute value of B, and minor axis absolute value of A minus absolute value of B. So moving on to a decomposition of our numerical range, we recall that the composition operator itself can be broken up into different restrictions on these H spaces. So the numerical range of it equals the convex hull of the union of the point 1 with the numerical range of CA restricted to these homogeneous polynomials of degree 1 through infinity. This leads us to a theorem from last year's composition operator group. So letting A again be a 2x2 antediagonal matrix, the numerical range of our composition operator restricted to some HK space is equal to the numerical range of this matrix here. Furthermore, the numerical range of CA restricted to homogeneous polynomials of degree 0 is simply the point 1. This theorem makes it much easier to compute numerical ranges of these restricted spaces. As you can see here, we plotted on Mathematica the ellipses corresponding to the numerical ranges of our restricted subspaces for K equals 1, 2, 3, and 4. However, we know that there are infinitely many subspaces of homogeneous polynomials, which still makes it difficult to compute. Which leads us to our theorem for this year, where we find an easier way to calculate the numerical range. So supposing A is once again a 2x2 antediagonal matrix where A and B are between -1 and 1, not equal to each other, but have the same sign, we can compare minor axes in order to find the last contributing ellipse to the numerical range. So our goal is to find the ellipse that is larger with a minor axis larger than both its predecessor and the ellipse that comes after it. In this illustration, we can see this third ellipse, the green one, has the largest minor axis, and it is therefore the last ellipse that contributes to the numerical range. Thus, the numerical range of this composition operator shown in the picture is going to be the convex hull of the union of the point 1 with the numerical range of our composition operator restricted to H1, 2, and 3. This red one here, red ellipse, is redundant. So on this slide, we have plotted our restrictions by minor axis. So letting A be on the horizontal axis and B be on the vertical axis, we can easily tell which ellipse is going to be the last one to contribute by plotting A and B as an ordered pair. So remember from our last slide, the last contributing ellipse was at k equals 3, this green band here, which means that our A and B, when plotted as an ordered pair, will be between this green ellipse and the red ellipse. So in this area where my cursor is. And we could do that for any given A and B, or we could find an A and B such that it is between two desired curves. However, we didn't just work with the 2x2 case, we worked also with the 3x3 case, and that proved to be much more challenging. So this picture represents the numerical range of a 3x3 composition operator on H5. And it not only gives us 1, 2, 3, 4, 5 ellipses, it also gives us ellipses and other points inside of those ellipses. And this is just for a single space of homogeneous polynomials, which makes this very difficult to work with. Nevertheless, we did come up with a theorem to help us compute the numerical range for the 3x3 case. So supposing A is a 3x3 antidiagonal matrix, where A, B, and C are all between 0 and 1, and they're not equal to each other. If B is less than or equal to C plus A over 2, and C plus A is less than or equal to 1, then the numerical range of our composition operator is simply the convex hull of the union of the point 1 with the numerical range of CA restricted to the homogeneous polynomials of degree 1. This illustration shows what such a composition operator could look like. And with that, I will send it off to Georgia.
All right, so Tim just went over calculating the numerical range of when A is a 2x2 and a 3x3 matrix. And so now I'll be going over a theorem that we found for when A is a 2x2 matrix, and then what we found when we generalized it to the n by n case. So first of all, recall that the numerical range of the composition operator restricted to the homogeneous polynomials of degree 0 is just a set 1, and that the numerical range of the composition operator is the convex hull of the union of the numerical range of the restricted composition operators. So a couple things to note. First, that the composition operator is unitary if and only if A is unitary. So for a 2x2 antidiagonal matrix, it is unitary when the modulus of A and the modulus of B both equal 1. Second, the orthogonal complement to the homogeneous polynomials of degree 0, or I will be referring to it as H0 perp, is the direct sum of the homogeneous polynomials of degree j for j equals 1 to infinity. And lastly, an antidiagonal matrix A is unitarily similar to the direct sum of 2x2 matrices. And so I kind of want to go over the main motivation behind this theorem before we begin. So we first noticed that the point 1 would always be included in the numerical range because of that restriction to H0. And we want to see when that would also occur when restricting to H0 perp instead. So the theorem that we found states that we let A be a 2x2 antidiagonal matrix, then the numerical range of the composition operator restricted to H0 perp intersects the unit circle if and only if the composition operator is unitary. So I'm just going to quickly go over the proof of this theorem. We let e to the I theta be in the numerical range, which is just the convex hull of the union of infinitely many ellipses. And because e to the I theta is an extreme point of the unit disk, e to the I theta must lie on one of these ellipses for some j, and that the major axis of that ellipse must equal 2. Because we already have the condition that the modulus of A and the modulus of B both have to be less than or equal to 1, we are left with that the modulus of A and the modulus of B both equal 1. And because of that, we can show that A is unitary, and thus the composition operator is unitary as well. And the reverse direction of this theorem can easily be shown in a similar fashion. And so when we're generalizing this to the n by n case, we found something very similar, just not as precise as the 2 by 2 case. So the theorem that we found states that we let A be an n by n matrix that is the direct sum of these 2 by 2 blocks. Then the numerical range of the composition operator restricted to H0 perp intersects the unit circle if and only if the composition operator has a reducing subspace on which CA is unitary. So again, a couple of things to note. Another way to think about this theorem is that there must exist a 2 by 2 or a 1 by 1 block in the matrix representation that is unitary. And this theorem implies that there exists a 2 by 2 or 1 by 1 block in the matrix A itself, which is also unitary. And so the heart of this proof for the n by n case really lies in the 2 by 2 proof that I previously went over. So now I'm just going to quickly go over an explicit example to show the similarities and how the 2 by 2 proof is used. So we let A be a 4 by 4 matrix made up of 2 by 2 blocks. We let e to I theta be in the numerical range. And for the same reason as the 2 by 2 proof, e to the I theta must lie on one of these ellipses, and that the major axis of that ellipse must equal 2. And so now we get to 3 cases. So for case 1, where alpha 2 and alpha 3 equal 0, we are left with A1, alpha 1, A4, and alpha 4 terms. And because of that, we can go back to the 2 by 2 case, and we can prove in a similar way that a block in the matrix representation and a block in the matrix A is unitary. And the same can be said for case 2, where alpha 1 and alpha 4 equal 0. And then when we get to case 3, where neither the pairs alpha 1 and alpha 4, nor alpha 2, alpha 3 equals 0, we can show in a very similar way as the 2 by 2 proof that a block in the matrix representation is unitary, but instead of just a block in A is unitary, the entirety of the matrix A must be unitary. And so I hope that you were able to see that the heart of the n by n proof really lies in the 2 by 2 case. And so today we went over the composition operator induced by an anti-diagonal matrix, the matrix representation of the composition operator, as well as calculating the spectrum and the numerical range of the composition operator. And so we would like to thank the National Science Foundation and the National Security Agency for funding this research, as well as the University of Michigan-Dearborn. So thank you so much for listening to our presentation.